So let's go ahead and find a general formula for the sum of the first n even numbers. Positive even numbers, I should stipulate. So we can go ahead and define a sequence a sub n, okay, as of course 2, 4, 6, 8, 10, 12, so on and so forth. Okay. And then we want to define S sub n as the sequence of partial sums. So we have 2. We've got 2 plus 4, which is 6. 2 plus 4 plus 6, which is 12. And then plus 8, which is 20. Plus 10, which is 30. Plus 12, which is 42. Okay. Now to describe a pattern here, we're going to want to find a constant difference, whether it's a constant first, second, third difference. We don't know yet, so we're going to have to try to figure that out. So the first, to get to 6 from 2, you add 4. To get to 12 from 6, you add 6. This is obvious, right? This is just the numbers in question here. Let's go ahead and fill this out then. Okay. So we see we don't have a constant first difference. Of course, if we did, we would have a linear growth pattern, an arithmetic growth. Okay, I should say arithmetic since we're talking about discrete functions here. We're not talking about continuous functions. Whole different kind of math. Okay, now if you take a look carefully, you can see that we are indeed going to have a constant second difference. Okay, we are indeed going to have that constant second difference. And remember, a constant second difference indicates a quadratic relationship. Okay, which of course can be modeled by an squared. Well, let's define it first. S sub n equals an squared plus bn plus c. Of course, we know n is restricted to the positive integers. Okay, this is a discrete function here. Okay, so good. If I plug in 1, I should get 2, since 2 is the partial sum, the first partial sum. If I plug in 2, I should get 6, and 6 is the second partial sum. If I plug in 3, I should get 12, since 12 is the third partial sum, and 4, 25, 36, 42, so on and so forth. Using this model, which we know is valid since we have this consistent constant second difference, so I can say here a times 1 squared plus b times 1 plus c equals 2. Okay, again, and when n is 1, S sub n is 2. Moreover, I should have a times 2 squared plus b times 2 plus c equals 6. Okay, again, when n is 2, c is S sub n is 6. And moreover, I should have a times 3 squared plus b times 3 plus c is equal to 12. Okay, since 12 is the third partial sum. So I have this nice system. I don't need any other set of inputs and outputs, given, of course, that I have only 3 unknowns that I'm looking to solve for, a, b, and c. Let's go ahead and simplify this. So it's going to give us here a plus b plus c equals 2. 4a plus 2b plus c equals 6. 9a plus 3b plus c is equal to 12. Okay. Now, I'm going to go ahead and solve for c for all of these. And if you've watched some of my other videos dealing with this concept, you'll notice that I do consistently solve for the constant when its coefficient is 1. Or sorry, not the constant, but the variable whose coefficient is 1, in this case c. So let's subtract a and b from both sides. I'm going to have c equals 2 minus a minus b. Here I'm going to have c equals 6 minus 4a minus 2b. Here I'm going to have c equals 12 minus 9a minus 3b. And now I can set c equal to itself. I'll set the first equation equal to the second, and I'll set the second equal to the third, and I'll reduce a 3 system to a 2 system, making our lives a lot easier here. So c is equal to c after all. I got 2 minus a minus b equals 6 minus 4a minus 2b. And then I've got, of course, 6 minus 4a minus 2b is equal to 12 minus 9a minus 3b. Okay, very good. Now, checking that very carefully. Yes, that looks good. So let's go ahead and put both of these into standard form. Let's add 4a to both sides. Negative a plus 4a is 3a. Let's add 2b to both sides. Negative b plus 2b is going to be b. And then subtracting 2 from both sides. 6 minus 2 is 4. Okay. And then for the bottom equation, let's go ahead and add 9a to both sides. Negative 4a plus 9a is 5a. Adding 3b to both sides. Negative 2b, plus 3b is b. And then subtracting 6 from both sides. 12 minus 6 is 6. Checking that ever so briefly. Very good. Now, as you can see, we're perfectly set up for elimination. Let's go ahead and do that. 3a minus 5a is negative 2a. 4 minus 6, negative 2. And clearly, we're going to have a equals positive 1. Okay, let's go ahead and find b. We know that using this top equation, that 3 times 1 plus b is equal to 4. That means that 3 plus b equals 4. Subtracting 3 from both sides, that means b equals 1. Okay. Now we got to find c. Let's go ahead and just use this top equation. We've got c equals 2 minus a, which is 1, minus b, which is also 1. Well, that means c equals 0. Okay. So we're done. So we have s sub n is equal to a, which we've discovered to be 1, times n squared, plus b, which we've discovered to be 1, times n, plus c, which is 0. Clearly the 0 doesn't matter. And what do we got? We've got n squared plus n, which is sometimes expressed as n times the quantity n plus 1. There you go. A formula for the sum of the first n positive even numbers. We love doing math around here. We're going to prove as many statements as time permits. I have a big list of statements I want to prove, but I'm sure there are many more out there that I haven't thought of, and I trust that our loyal viewers will submit questions and prompt me in a certain direction. Have a great time studying math. We love math around here and physics. And again, we're going to try to prove as many statements as we can. Have a great rest of your day.